determining a chemical formula from experimental data. This is how empirical formulas are determined. So we can determine it from elemental analysis. We can take a compound and decompose it into the individual elements and measure the masses of the elements. Or we can measure the masses of the elements that combine, react to form a compound. We can also determine an empirical formula by knowing the percent composition. So we need to remember an empirical formula represents the ratio of atoms or ratio of moles of atoms. It's not the ratio of the masses. So we have to take mass information and get it into moles before we can look at ratios. So here are steps. Some people like a list of instructions to follow. I wish I had one of those for my life, right? If you don't like lists, you can just skip over this. First thing is you need the masses of each element. So sometimes it says mass of this, mass of hydrogen is that, and so you just write them down. Sometimes it gives you a percentage. Okay, so it says, well, it's 15.2% oxygen. What do you do with that? How do you get a mass? Well, again, we're going to choose a useful, convenient amount. If we choose 100 grams as our sample size, then the mass of the element is the same as its percentage. So if it gives you a percentage, just knock percent off and change it to grams. We need to convert each of those masses to moles using the molar mass for the element. And then we need to get ratios. So your book talks about writing a pseudo formula using the number of moles. I kind of think that's dumb. What we're going to do is we're going to skip number 3. We're going to divide all of the moles. So we've got moles for each element, and we're going to divide all of them by the smallest number of moles. We want a whole number ratio. Moles of this to moles of that to moles of that. Because this is based on experimental data or made up experimental data, the numbers are not going to come out perfectly because there's some uncertainty there. Okay? Most compounds are going to have relatively low whole numbers. We're not going to have like 297 carbons to 594, not really big weird numbers. We're going to have small numbers like 2 and 6 and maybe 10. So when you look at those ratios, this is my guideline. If the result is within 0.2 of a whole number, you can round it to the whole number. That means if it's 1.2, you could round that down. I prefer that 1.2, that's getting a bit iffy. But if it's 1.19, you can round it down to 1. If it's 1.22, you can't. Okay, that's getting too close to 1 1/4. If it's 1.95, that's only 0.05 away from a whole number. You can round it up. So we can do a little bit of rounding, but we can't just round to the nearest whole number. We'll get the wrong answer. If you can't round to whole numbers, then you need to multiply all of those subscripts, all of the ratios, by the same small whole number, so that you get small whole number ratios. And there are fractional equivalents for, decimal equivalents for fractions, right? So this is 1/3. This is 1/4. This is 1/5. You get the idea. So if don't do that. If it's got, if you end up with 2.20, well, if you multiply by 5, you're going to get a whole number. If it ends in 0.25 or close to it, you're going to multiply by 4. So if you recognize those, you can choose which number to multiply. A lot of students don't recognize that. That's fine. Here, the trial and error method works pretty well. If they're not coming out whole numbers, try multiplying them all by 2. If that works, awesome. If it doesn't, try 3. Try 4. Try 5. You shouldn't have to go any farther than that. So let's do some examples. Sample of a compound is decomposed in the lab produces 165 grams of carbon, 27.8 grams of hydrogen, 220.2 grams of oxygen. Calculate the empirical formula. So here we are given the mass of each element. So we need to write that down. 165 grams of carbon and 27.8 grams of hydrogen and 220.2 grams of oxygen. That's the first step, get masses of each element. We need to convert these into moles because the formula gives ratios of moles, not ratios of masses. So we use the molar mass of the element to change it to moles. So I want to get moles of carbon. I need to divide by grams of carbon. 1 mole is 12.01 grams. So we're using those molar masses from the periodic table. Based on the starting number, this would have 3 significant figures. This is a place where more digits are better. Things are going to get rounded off to whole numbers at the end anyway. Always keep some extra digits here. So that would be the 3 sig figs, and I'm just going to keep 2 extras because it's a good idea. So that's moles of carbon in this particular sample. For hydrogen, I'm going to multiply by 1 mole of hydrogen over 1.008 grams of hydrogen. That's the molar mass. And don't round that to 1. So this is going to be, 27.579 moles of hydrogen. And then for oxygen, 1 mole of oxygen, 16.00 grams. So 220.2 divided by 16. And this gives me 13.7. Well, that one's got 4 sig figs actually. 7625 moles of oxygen. So your book says, well, make a pseudo formula. So it's C 13.738, H 27.579, O 13.7625. Those aren't whole numbers, right? I don't like that, so I'm not going to do it. So I've got moles of each. I need ratios. And my ratios, I need to end up with whole numbers larger than 0. So what I want to do is I want to identify which of these is the smallest number, and I'm going to divide them all by the smallest. So in this instance, the moles of carbon is slightly smaller than the moles of oxygen. So I'm going to divide all of them by the smallest, 13.738. So that gives me 1. And I'm going to divide this by 13.738. 27.579 divided by 13.738 equals. That came out to 2.0074. When you divide the smallest by itself, that's always going to be exactly 1. And then the others are going to have some digits on them. And I'm going to divide this by the smallest. I have to divide them all by the same thing to preserve the ratio. And so this one comes out to 1.00178. So this number is very close to 2. The difference between this and 2 is less than 0.2. So I can round this to 2. I can say that's equal to 2. And this number is very close to 1. The difference between this and 1 is less than 0.2. So I can round that to 1. So now I've got 1, 2, and 1. These are the subscripts for these individual elements. So carbon 1, hydrogen 2, oxygen 1. Except, of course, we don't write the ones. So I'm going to get CH2O. That's the empirical formula. Any questions? Yeah. You always divide by the smallest. When you divide by the smallest, then these ratios that you get, the smallest will be 1. And everything else will be either really close to 1 or larger. If we end up like with 2.5 here, we need to multiply all of them by 2. We'd end up with 2, 5, and 2. Let's do another one. Old friend, ibuprofen. This is my, when my kids come and complain about anything, my elbow hurts, I have a headache, I don't feel good. That's my answer. Take some ibuprofen. Solves everything. Here we're given percent composition and asked to find the empirical formula. So they're not giving us masses. But if we choose to think about 100 grams of this, 100 grams will have 75.69 grams of carbon. So we can just take these numbers and write gram instead of percent, and we'll be good. So for carbon, we got 75.69 grams of carbon and 8.80 grams of hydrogen and 15.51 grams of oxygen. We need to convert these to moles. So 1 mole of carbon over 12.01 grams, 1 mole of hydrogen over 1.008 grams of hydrogen, 1 mole of oxygen over 16.00 grams of oxygen. These get a little tedious. There's a fair amount of tedium in science.
And is that the denominator for the conversion factor out?
Good question. So where am I getting this? This is the molar mass of carbon. I'm getting the 12.01 from the periodic table.
Okay.
So for carbon, for hydrogen, for oxygen. It's a messy 16. So when I convert grams of carbon to moles of carbon, I get 6.3. I want to keep 4 sig figs. So that's moles of carbon. .7301 moles of hydrogen. You don't really have to keep track of sig figs here. You just need to make sure that you include enough. 15.51 divided by 16. This comes out to be 0.969375 moles of oxygen. I convert grams of each element to moles of each element. Then I see which one's smaller, and I divide all of them by the smallest. So this is the smallest one, right? So I'm going to divide that by itself. And that one's going to end up being 1. And then I'm going to take this one and divide by the smallest. So 8.7301 divided by 0.969375. So this is 9.0059. Oh, that's looking nice. And I'll take this one and divide by 0.969375. 6.30224 divided by 0.969375 equals, and this one comes out to be 6.501 and 4. Can I round this to 7? Nope, not close enough. Could I round this to 9? Yeah, I could. And this is exactly 1. But I'm not going to round this because I have to multiply this one. So I recognize that 0.5 is the decimal equivalent of the fraction 1/2. This is 6.5. If I multiply by 2, I'm going to get a whole number. If you don't recognize that, just try 2. So I've got that 6.50134 in my calculator still. I'm going to multiply by 2. Oh, nice, right? So times 2, now I get 13.0026, blah, blah, blah. That can be rounded to 13. So this is 13. If I do times 2 on one of them, I have to do the same thing to each of them. Otherwise, I'll be changing the ratios. So this needs to be times 2. What's that going to round up? Well, let's just do it. So I do that one, and I get 18.0118. That is also close enough to round, so that's 18. And then this one, I also have to multiply by 2, and so I'm going to get 2. Now I've got my whole numbers. 13, 18, and 2. That is the lowest whole number ratio. I had to multiply by 2 because 6.5 to 9 to 1, although it is the same ratio, isn't whole numbers. And I can't have 6.5 atoms of carbon. So the carbon has a subscript 18, hydrogen has, 13. I said 18, wrote 13. Something is wrong with my head. Hydrogen is 18, and the oxygen's 2. So that's the empirical formula. That's the lowest ratio of carbon to hydrogen to oxygen. Any questions?
So we put the order of those, just with like what we're given, carbon, hydrogen, oxygen. So
Yeah, so how do you know, should I put carbon first, hydrogen first, what should I do? They're usually going to give it to you in the correct order. I don't know if they do that on purpose or it's just because that's how we think about it. I would say just do whatever order they give them to you, put them in that order. I'm not going to try to trick you on stuff like that. Yes?
Why did you multiply by 2?
Why did I multiply by 2? Good question. So when I got my ratios by dividing by the smallest, 6.5 is like right between 6 and 7. It's not within 0.2 of a whole number, so I can't just round it off. So then I need to multiply by something to get a whole number. In this case, it was 2. Any other questions? That gives us the empirical formula. How do we get the molecular formula? The molecular formula tells us how many atoms of each element are actually in that molecule. And that's the most useful formula. So the molecular formula is always going to be a multiple of the empirical formula. They can be the same, so then the multiple is 1, or you may have to multiply by 2 or 3 or whatever. In order to figure that out, you need to know the molar mass of the compound. That will have to be given to you. That's the sort of thing that's determined often by mass spectrometry. We figure out the molar mass of the compound, and then we figure out the empirical formula, and then we can put them together to get the molecular formula. So we can say that the molecular formula is equal to the empirical formula times some integer. We need to know what n is. So we can take the actual molar mass that we're given and divide by the molar mass of the empirical formula, and that'll give us a whole number. That's what we need to multiply all the subscripts by. So here we have a compound that has the empirical formula CH and a molar mass of 78.11 grams per mole, and we're asked to find its molecular formula. On worksheets, they'll give you percentages, make you calculate the empirical formula, and then make you calculate the molecular formula. This one's a shorter one. So we've got this empirical formula, and this is the molar mass of the molecular formula. So we've got CH, And we're given this 78.11 grams per mole. So what I want to know is how many times does CH fit into the molecular formula? Well, what does this empirical formula weigh? Can we calculate the molar mass of the empirical formula? Sure we can. It's the mass of carbon. There's one carbon plus the mass of the hydrogen. And so that's 13.018. So that weighs 13.018 grams per mole. How many times bigger is this than that? Well, do division. So that N, that multiplier, is going to be the 78.11 grams per mole, the actual molar mass, divided by the molar mass of the empirical formula. So 78.11 divided by 13.018 equals. My calculator is telling me 6.00015. We will never have to multiply this or do anything with this. This should come out very close to a whole number. So that's going to be 6. This tells me that the molecular formula is 6 times as big as this. So it has 6 times as many carbons, 6 times as many hydrogens. So sometimes we'll sort of show what we're doing by doing this. We're taking that empirical formula, we're multiplying it by 6. This is not a good answer. That's just like a thinking, showing how we're thinking sort of thing. And so this is actually C6H6. That's the molecular formula. Any questions? Combustion analysis is another way to figure out the empirical formula. You take a known mass of a compound and you burn it, and then you collect and weigh the products from the combustion. And this is frequently used for compounds, organic compounds that are carbon, hydrogen, and oxygen. It's not very useful on other sorts of compounds. So we know the mass of the product and the composition of the constituent element in each of those products, and then we can figure out the original amount of the element. So what happens in this combustion is all of the carbon that was in the original compound forms CO2. So we know the mass of CO2 that's released, and we can figure out the mass of carbon that's in that CO2, and that's the mass of carbon that was in the starting compound. All the hydrogen forms water. So we collect that, we weigh it, and then we can find the mass of hydrogen. The original mass of oxygen, if there is any in the compound, is found by subtracting. You know the total mass that you started with. You've calculated how much carbon was released, how much hydrogen was released. Any difference must be oxygen. This is a picture of illustration of the type of apparatus. So you've got a furnace with the sample in here, and in order to combust it, you need to provide oxygen. So we've got oxygen gas going in here. As this burns, the gaseous products leave the furnace and go through these U-tubes. The first one has a substance in it that's going to absorb the water from the air as it goes through. So they weigh this tube before and after analysis. It's going to be heavy afterwards because all of the hydrogen that was in this sample became water and got stuck in that absorber. CO2 does not get absorbed by this, and so it continues on and it gets stuck in this tube. And again, we weigh the tube before and after, and we can figure out the mass of CO2. We can't measure directly the mass of oxygen because we had to put a whole bunch of oxygen in there to make the thing burn. So we just figure out the oxygen by difference. Okay, upon combustion, a compound containing only carbon and hydrogen produce 1.60 grams of CO2 and 0.819 grams of water. Find the empirical formula of the compound. So we know we've got just carbon and hydrogen. So we're given, we're given the mass of CO2, and we're given the mass of water that are formed. This CO2 has all of the carbon in it from the original compound. So I need to figure out, ultimately, the moles of carbon that are in that mass of CO2. So first what I want to do is I want to convert grams of carbon dioxide to moles of carbon dioxide. And then I can use a ratio I get from the formula. There's 1 mole of carbon in every mole of CO2. So what I'm doing is I'm taking grams to moles and then to moles of the element. So I've got moles of CO2. I need grams of CO2 down here. And then I want to find moles of carbon. So I need to divide by moles of CO2. Well, this one's easy. This is from the formula. There's 1 carbon in 1 unit of that, so there's 1 mole of carbon in 1 mole of CO2. But then I need the molar mass of CO2. So 1 mole of CO2 weighs 44.01 grams. 1.6 divided by 44.01 equals times 1 divided by 1. So I'm getting 0.0365355 moles of carbon. Here, grams of water. So the hydrogen in here is what I'm interested in. So I need to convert this from grams of water to moles of water. In the interests of saving time, I'll just tell you the molar mass of water is 18.016 grams. And then I need the ratio of moles of hydrogen to moles of water. How many moles of hydrogen are in 1 mole of water? 2. H2O. So 0.819 divided by 18.016 times 2. So this gives me 0.090919 moles of hydrogen. Those are much smaller numbers than we had before, but that's fine. What do I do now? I divide by the smallest. So 0.03 is smaller than 0.09. So I'm going to divide by that. So this one's going to come out to be 1. I'm going to divide this one by that same number, 0.036355. And that's going to give me 2.50087. What do I do with that? 2.5. I need to multiply by 2. If I multiply this by 2, I'm going to get 5 something, right? 5.0017. Okay, so I can call that 5. If I multiply this one by 2, I have to multiply the other one by 2. And 1 times 2 is usually 2. So I'm going to get C2H5. Any questions? You should have had how to calculate an empirical formula in Chem 3A or your other prerequisite. This one, we don't teach combustion analysis in Chem 3A. It's a little more complicated. This is a higher level class. There's another example. I don't know about you, but I'm tired. So I think we'll do this one next week, and that'll be kind of a good review. And then we're going on to chemical reactions, which kind of doesn't seem to belong in this chapter, so we'll just push it off.